Okay.
I can.
So hi everybody, I'm Megan Zimmerman. I work at NIST. I am the co-lead for the AI for Manufacturing Robotics project at NIST, and the MOAD dataset, Manufacturing Objects for Assembly dataset, is sort of my brainchild, and I'm very excited to announce the release of the first version of this dataset, which includes the first ATB today. So let's see. Disclaimer, really quick, I am legally obligated to say that all commercial equipment and materials identified in order to adequately specify certain procedures. In no case does this such identification imply recommendation or endorsement by the National Institutes of Standards and Technology, nor does it imply that the materials or equipment identified are necessarily the best available for the purpose. Now that that is out of the way and the legal people will not get mad at me, I want to talk a little bit about why we're making this data set. So there's a number of object data sets already for robot manipulation that you may be familiar with. Most commonly known is the YCB Common Objects dataset from 2015, but there's also the Fraunhofer IPA bin picking dataset, DexNet, and the Selene dataset. All of these datasets are excellent. Some of them are a little bit outdated since it's been almost 10 years since YCB, but there is very limited representation of assembly tasks or production tasks, and updates to these datasets are few, if any, especially for the YCB dataset. Part of this is because of the documentation issues, which I will get into in a moment. So the big motivation here was that manufacturing and assembly is a highly requested area for robotic manipulation advancements, but frequently it doesn't get enough attention because it's not necessarily the sexy world shaping stuff like service robotics or other things like that. But still it is necessary and more immediately applicable, and also provides a good benchmark for an environment where robot manipulation is more immediately applicable. So the limitations in dataset replication. So we noticed with the YCB dataset that the documentation was not the best, and as Adam will tell you, as the person who is now maintaining the YCB dataset, we just did not have access to update the dataset over the past few years. Things come in and out of the supply chain, so some of the objects that were available 5 years ago are not available in the same way now. The packaging may look different. It just may not be accessible, so they need to be replaced with different objects, but we can't replace those scans if we don't have the documentation and the facilities to do so. So a lack of thorough detail because of page limits for publications was, I think, a huge issue here. So you publish your paper in a conference and you don't necessarily have access to all of the space you need to adequately represent your system, which means that you don't have that system to be able to be replicated later on. Another issue was institutional changes and turnover. So after YCB was created, it was no longer novel work. So maintaining a data set was difficult and was passed over to UMass Lowell. This is an issue with a lot of data sets, especially ones made by academia, because the structure is just not there to support continuing support for dataset maintenance. Issues with tech transfer, and then it's difficult for academic faculty to maintain datasets for long term and justify that labor cost. Mostly because you need to keep on publishing, right? And you can't just stick on the same thing over and over again. So one thing you'll notice, which I spoke about a little bit earlier, so here's a Cheez-It box. This is the Cheez-It box from the YCB collection, the initial collection in 2015. And then this is the Cheez-It box today. It looks similar, but it is very different, which may cause issues with, image recognition systems. Overall, not great that they're not the same. And because we can't update them, we need to, be able to update them to maintain a data set, right? The fact that the Cheez-It box from 2023 to 2015 is different is a huge pain in the butt to anybody who is maintaining a data set. And a lot of this is, again, supply chain issues, right? And this is true for most data sets, especially ones that are using commercially available materials. Even the task boards today have changes that need to be updated because of the supply chain changing and not having access to certain parts of materials. So the goals for this were to thoroughly document the collection rig and the process and provide an upgradable collection rig and open access software for collection. Have a long-term plan for maintainability and the ability for expansion as needs change in the community, and provide plans to update timelines and criteria. And then finally, representation of realistic assembly tasks across multiple industries and the inclusion of community requested items. So the idea here is to involve the community and ask them what they would like objects included, and update and add things over time. So it's not just going to be the task board. There are other objects selected for collection that will be released later on, and we will include more as needed by the community. So a little bit about the open source principles that we adhere to guide our process here. There are a few things that the open source principles provide to us that enable better data sets over time, primarily transparency. So having documentation that is thorough and elaborate, but still cohesive and available, is important to make sure that if somebody wants to make their own data set later with the same methodology, they absolutely can. So it's not a locked process. It is open to all. Collaboration. So we want to make sure that we involve industry and academia together and assess their needs and try to provide the objects needed to address them. And then release early and often. So releasing early right now because the initial data set is the task board, but we intend on adding many, many more objects over time and updating it iteratively as sensors improve and as data needs to be updated when items change and as needs change in the community. And then making sure all voices are heard. So if others are interested in replicating the process and then maybe even improving it, we are always open to feedback and input. And then again, asking the community for involvement, holding competitions for the task boards, and eventually the larger data set and direct collaboration. So this is the rig that we are using to collect the data with. There are 5 points of collection. At each point, there is a high-resolution DSLR RGB camera with a zoom on it for smaller objects. There is a Intel RealSense RGB-D sensor, so 5 of these, right? And then a laser alignment mechanism to make sure that the center of the plate is aligned with each object and each camera. And then there are 2 options of motor for this. Right now, the documentation is available for the cheaper option of motor that may be a little less reliable, but it is more accessible. So we have a higher budget motor and a lower budget motor to address different budgets. 2 lighting panels, a green screen background, and plate. This is so that you can segment out the plate and the background easier, and also replace the background of each scene with whatever you may need to increase rigidity of your models. So if you want to replace it with this is a common practice now where you increase the rigidity of your model by adding in randomized backgrounds to allow better recognition with different occlusions in the background. 2 lighting panels to ensure that the lighting is consistent from all angles, not mentioned here. And then a lux meter for the metadata for the ambient light in the room for the collection. So For each part, a subassembly and assembly, a laser is used to calibrate the center of the table. A lux meter sample is taken before collection. And then the DSLR cameras are zoomed to the focal point, inclusive of the largest area around the object possible for the full rotation. And that focal point is recorded on the zoom. And then every 5 degrees, a sample is taken from each camera, so along each angle, and then each depth sensor, so each real sense camera at each of the 5 angles. This results in 72 turntable positions and 360 RGBD point cloud samples. The reason why we chose 5 degrees was because while the YCB dataset was every 3 degrees, we felt it was a little bit redundant, and the dataset is already pretty large for each object. So this provided us the same reliability, but with a smaller data footprint. So I guess I'll talk a little bit about the ATBs, right? So the NIST ATBs are a series of assembly task boards for benchmarking robot systems and their ability to perform manufacturing specific tasks. There are several ATBs at NIST. The one we are focusing on here today is the NIST ATB-1, which provides a number of different rigid materials for assembly, from pegs and holes to cable insertions, so the USB, the Ethernet, the screws, and then the gear meshing. The benchmarks here are pretty well established. This has been a competition that's been run for the past several years at both ICRA and IROS, and I think will be run again at IROS. I don't think we're doing ICRA this year. Correct me if I'm wrong. So the idea here is that it's a reproducible test method with a predefined artifacts and an established protocol to produce reproducible test data, and in a way that is reflective of how things actually work for manufacturing robotics. Okay, so we like the task boards a lot, but we wanted to make sure that we included things that represented different areas of manufacturing. We looked at the US Census Bureau for different forms of manufacturing and decided the relevant domains that were at a mature enough level to have data taken for there to be impact. So we selected the automotive industry, electronics industry, and furniture manufacturing industries. And the objects that we selected were selected based off of the following criteria, which is the diversity of the task complexity. So all of these assemblies are of varying levels of complexity. So some are much easier than the others, and some are very difficult. The ability to be reused and reassembled, so you can disassemble and reassemble these without it being destructive in the disassembly or reassembly. This is so that for furniture, for example, when you have wooden furniture where you are building and taking things apart, wood screws are destructive, right? It does damage the point where you are screwing into it. So if you want to take that apart and put it back in, the hole where the wood screw goes into is going to be looser, right? To avoid having a bunch of assemblies of the same object in your lab piling up over time, we wanted things that were reusable and a little bit more economical. We wanted them to be representative of the domain. So we tried to avoid things like toys that represent a manufacturing task. There is still a model, but it is a very detailed model, and not necessarily, I would say, a toy. And then we wanted things that were supposed to have a longer market distribution lifespan. So as we said before with the Cheez-Its, the things may or may not change, but we wanted things that would stay around for a little bit longer to avoid having to retake data as much as possible. But we are still planning on retaking the data as we see that these objects go in and out of the distribution lifespan. And then the ability to be substituted and replaced. So when that product goes out of the market, the ability to find a similar product and replace it with that was important to us, so that it didn't just end up dead in the water. And making sure that we document when this happens and why it happens is, I think, also important. So we can sort of see the market trends here of when these objects come in and out of the lifespan and how much we'll need to replace over time as we see this pattern. And then all of this is with the goal of being as representative as possible, while also being sustainable and addressing technical needs. And that's one of the objects. So as of right now, we have a few objects selected for the next round of collection. This is the model car engine, which is our most complex object. A small metal drawer assembly, a desktop computer, a fan, and a small wooden cube piece of furniture. We are actively seeking input on additional objects to be collected for subsequent collection beyond this, but this is the initial set. The variety here is coming from just how complex these objects can be. So the car engine, for example, has over, I think, 250 different pieces, whereas the fan has maybe 5. So it's a much easier assembly versus the most complex assembly. Okay, so the data that we are releasing today includes the bill of materials for the assembly, the manufacturer provided CAD files when available. So all of the pieces on the task boards that you can find in the back of the room have the CAD files available for them. I think for the most part, except for maybe the Ethernet plugs and the USB plugs, just because of how difficult it is to represent that in CAD with the flexible materials, right? There are 360 RGB images per sample, 360 depth images and point clouds per sample, the data collection software, and the full documentation and instructions for replication of this rig, so you can collect your own data if necessary. Again, you can also contact us and let us know your needs, and we can see what we can do to try to add it to the data set later on. And then, the image, the video to play. So this is an example of the point cloud here for the car engine. The car engine, again, is not included in this current release, but you will find the same point cloud collection of the task board on the website. So scheduled editions. We want to make this as accessible as possible. We also want to provide the same amount of detail that YCB did, maybe even more. Segmentation masks for all the images are planned to be released. Texture mapped 3D mesh models. So that's, as you can see on the video, this is one of the texture mapped 3D meshes for the waterproof plug. And then URDF conversion for ROS, and simulation implementation and sample scripts, tutorials and demos for teaching to students and learning later on, just to make it as accessible as possible, as usable as possible. And then, where can you find this? You can find this at robot-manipulation.org/NIST mode. The full data set is now available for collection of the task board ATV1. The data.gov entry will be being processed shortly, and that will be what you can cite for your papers when you use this data set, which should be late July, early August. But you can download the full data set now for your use. And any requests for additional objects or questions or inputs, you can email me directly at mlz@nist.gov. Thank you for coming, and I'm very excited to release this data set. So if there's any questions, I can take them too. I don't know if I have time.
So you mentioned there are 360 images per object.
Mm-hmm.
Are they registered in the same frame?
Yeah, so you can find that in the metadata too. So we've provided the the quaternions for each position of each camera, which you can use to localize where the object is in that space.
How did you grab that pose of the camera?
So I think this is something that we did with the Intel RealSense cameras, and then we'll need to, I think, distort that by the offset. It's all documented in the GitHub page on the website. One of our staff made that code. I can't answer directly what
I see. But it sounds like grabbing that from the images, or like kind of doing the structure from motion deal instead of like having additional maybe Vicon.
Yeah.
Or okay, got it. Thanks.
Yep.
Hi, thanks for the talk. Could you say a few words on how can people use this data set for what kind of problem?
Yeah, so the idea here was to represent a assembly in a way that we haven't really seen done before, right? So there are all of these object data sets where it shows you something when it is completed and something where it starts, but this is one where we have all of the pieces to it. And then the plan is to, for at least the more complex objects, provide each part of the assembly, right? So you have an understanding of how the assembly changes as it is built. So for example, with the car engine, you'll notice that there are a bunch of different little pieces, right, that assemble into the car engine, right? So we take each sub-assembly. So through each step of the assembly, we are taking a collection of the entire thing. And the idea there is to represent how things change as you complete an assembly.
So just two things from the chat. One correction, that the next usage of the NIST ATV will be at ICRA 2024.
Okay, cool.
Thank you, Minas. And Minas asked, how do we deal with the reflections on the NIST board?
Yeah, so this is a known issue with the, it's plexiglass on the NIST task board. I think we are planning on maybe changing the board that we use for that. But we record the lux meter data for this reason, so you can sort of see where the metadata, like what lighting environments you're in for this application, and then maybe use filters to adjust for your own application. So you're going to have a different lighting situation in your own lab than we are going to have in our collection environment. And the idea there is that we can sort of use filters and additional processing to change what the images look like for your training. And then there should be ways to make this model more robust, right? But the idea here is to provide you with the data to use that, right? The tools to do it yourself.
Yep. And Minas, we have seen some instances of people reproducing the panel out of other material to combat exactly that issue. So it's something we're very aware of.
Yeah. I think I'll talk to Kenny about maybe making alternative boards for that.
And then Andra, sorry, I apologize, asked, is this something that's relevant for the CASE conference? Which I will admit I know very little about.
I don't remember what the acronym of CASE represents anymore.
I believe CASE is Conference on Automation, Science, and Engineering. I believe it's more industry focused, if anyone wants to correct me.
I would say it's relevant.
On that.
Yeah. I think it's highly relevant to the CASE conference. I think we selected the RSS conference to present this data set because it was close to the time frame we wanted to get it out, and also a good venue for this.
All right. Megan, thank you very much.
Thank you.